I hope you had a great lunch. We're starting our third session this afternoon. It'll be composed of two keynotes, one to the beginning, one to the end, and then in between we do have our short orals and our poster session. I'll give the details as we go. First of all, let me introduce you to Wojciech Samek. He's a full professor at the Department for Electrical Engineering and Computer Science at the Technical University of Berlin. And he's also the head of the Department of Artificial Intelligence to the Fraunhofer Heinrich-Hertz Institute, the Fraunhofer HHI, by which we've actually heard a presentation already in the morning. And in continuation of this, Wojciech will talk about concept relevance propagation as a mean for explainable AI. You're good to go, Wojciech.
Yeah, thank you very much. And thank you for the invitation. I have to apologize that I cannot be there in person due to some unexpected situation. I had to cancel my flight. But the good news is that the first authors of the paper, which I will talk about, are at the conference and also at the workshop. So you have a chance to talk to them. Let me share my presentation. Yeah, so I will talk about our recent work on a concept level explainable AI. So basically, when we think about it, we have now a decade of very rapid development in the field of explainable AI. We have seen methods such as SLIME, GradCam, SHAP, guided backdrop, and so on, which can compute explanations for individual predictions of a black box model. Basically, these explanations are also regarded as attribution maps. So they show which input elements, which pixels are relevant for an individual prediction. So one of the methods which I would like to introduce a bit more in detail, because it is relevant for what comes later in the talk, is layer-wise relevance propagation. So the idea of LRP is to explain in a step-by-step fashion, in a layer-by-layer fashion. So instead of explaining the whole prediction at once, explaining the input-output relation at once, we want to propagate the relevance values from the output to the input layer by layer. So for that, we need, so in this case, we have a prediction dog. So the output neuron RK associated with the class dog is activated. We have the prediction dog. And what we want to have is a back propagation of this relevance value to the neurons of the last lower layer. In this case, we need to determine the part of the relevance, the contribution of neuron J to the activation of neuron K. And this contribution is denoted in our formula as ZJK. So ZJK tells us how much neuron J has contributed to the activation of neuron K. And once we have these values, we can distribute the relevances from the last layer to the second last layer. And we can do it iteratively through the network. And there are different ways of how to determine and quantify these contributions. So one very simple way is just to take into account the activation values, AJ, and the connection between neuron J and K, the WJK values, the weights. And there is also some theoretical interpretation of this redistribution process, but I will not go into details here. So the important point of LRP is that we have this explanation, but we propagate these relevance values through the network. So we have not only the input, the attribution maps at the input, but we also know how much each channel of the neural network has contributed to the prediction. And this information we will use later on. So this is like one, I would say like one of the advantages of LRP, that it also gives you this additional information on what channels have contributed how much to the prediction. And we saw a lot of success stories with attribution maps. So, you know, all these examples that explanations have been used to detect some errors in the model, some biases. For instance, when predicting for images of a husky, the network tells you it's a wolf because of the snow in the background. Or in our work, we saw that an image classifier which predicts horse images was mainly looking at the copyright tag in the bottom left corner. Or there is also other examples where the melanoma was predicted not because of the melanoma itself, but because of some stuff, some ruler which the dermatologist painted on the skin. So all these kind of artifacts are often present in data, and explanations can help us to uncover and unmask these misbehaviors. However, the question is, do we really understand the explanation? So how informative are these attribution maps? And basically, in one of the tutorials which I gave, I was explaining this example. So here we have an age predictor. The woman is predicted 28 to 32 years, which is correct. And I saw on the right, you see the attribution maps. And what I always said is, oh, it seems that laughing is a relevant feature for being predicted young, because this woman is laughing. And you see on the attribution map that the teeth of this woman were highlighted as being relevant to the prediction. But at some point, someone asked me, how do you know that it's really the laughing? Maybe it's the color of the teeth. This woman has a very white teeth, and usually white teeth are also associated to age. But maybe it's some other features of the teeth. She has also very big teeth. Maybe this is also what the network learned to associate. So in other words, attribution maps only tell us where something is relevant, but they do not tell us what it is. They tell us something in the face, something at the mouth, but we don't know whether it's a color, whether it's a size, whether it's some texture. This information we kind of interpret as humans when looking at the attribution. And what we wanted to do in our recent work is to bridge this gap. So our paper From Where to What, where like the first two authors, Redouan and Max, are at the conference, tries to bridge this gap and also tell us what features are relevant to the network, how are they represented, and how do they occur in the inference. So how are they used by the network in the inference process? So let me go through the contributions of our work one by one. So we start with the old picture with the LRP explanation. So we see an image of a dog, and we see the prediction dog. And what LRP does, it computes this heat map, showing you that the eye is relevant and the snout of the dog is relevant. And this is like one in all explanation. So this explanation explains you everything, the whole prediction. But we know that deep networks, especially the higher layers of a deep neural network, encode concepts, human interpretable concepts. And let us assume that the channels which I highlighted here encode concepts fur, eye, snout. So we know that neural network channels are encoding these kind of concepts. And what we get here is one explanation explaining the prediction, like aggregating all the contributions of all concepts which are relevant. But what we thought is maybe we can compute conditional explanations. So by filtering the redistribution process and only letting the relevance flow through a specific concept. So in the formulas, this is very easy to do. You just need to add a Kronecker delta to the formula, and filter everything out which is not going through this concept. And in this example, I filter everything out which doesn't go through the concept channel I. And you see that the heat map is explaining the prediction dog, but conditioned on the concept I. And we can do this for all different concepts. So assume one of the channels is encoding the concept fur, one of the channels is encoding the concept I, and one is encoding the concept snout. Then you can compute conditional explanations for each of these concepts. And what you see, for instance, is that the global relevance for the concept fur is much higher than the total relevance of the concept I, which means that the concept fur is contributing more to the prediction than the concept I. And you wouldn't see it in this all at once explanation because the concept I is very much localized. So the values are higher relatively to the concept fur, which is distributed through half of the image. And by disentangling these explanations, you can explain the relevance of each of these human interpretable concepts with respect to the classification. And of course, the big question is, how do you know, or how do we know what concepts a channel is encoding? So here I just told you that this channel is encoding the concept fur, the other one is encoding the concept I, but how do we know this relation? And basically, this is a question which has been studied in computer vision for quite some time, where people try to understand what concepts are encoded by a channel. And this work can be found by the term activation maximization, where people try to synthesize an input which maximizes the activation of a channel, or find some examples in the data which maximally activate the channel. And what we propose in our work is not to use activation maximization, but to maximize the relevance, to find images which are maximally relevant for a prediction and not which are maximally activated. And the big advantage is that by that we include automatically the task context, because relevances are computed with respect to a prediction, with respect to the task, while activations only measure what only give you the images which maximally stimulate the channel, irrespectively whether they are relevant for the prediction or not. So this is the second contribution of our work. We propose to use relevance maximization to get some information about the concepts encoded by a particular channel. And the third contribution is more technical one. Once we have this reference images, what we do is we kind of zoom into the receptive field of the neuron. So we just consider everything which is relevant in the receptive field. And we can do a second path through the network and compute the heat maps, the attribution maps, telling us which part of the image is relevant for the prediction and which is encoded by this particular channel. And in this case, it's a color. You see that the color in this case is encoded by this channel which we have selected. And this color is relevant for the prediction. So this is a third contribution, and taken together, what we get is we can compute concept atlases. So in this case, we have a prediction bird or particular type of bird. And what we do first is we find the most relevant concepts, which means the channels in the upper layer, for example, in the last convolution layer, which have highest relevance values. And these relevance values we can get by LRP. So this is the first step. We find the most relevant concepts. Then we can compute conditional explanations, solving the where question, where something is relevant. And in this case, you can get a feeling like what these different channels which we found are encoding. But we can compute in the third step, we can get this relevance by relevance maximization, we can visualize which concepts these channels are encoding. And in this case, for example, you see the channel 10, the channel in the middle, is encoding color, red color. And from that, you can derive that red color is particularly relevant for the prediction of this bird. And the most relevant feature seems to be like this, this texture, the texture of the feathers of the bird. You see channel 210, the first one, is encoding leopard-like texture, and this channel is highly relevant for the prediction. So basically, the advantages of our approach is that it's totally post hoc, so you can get a model and analyze it. You do not need to retrain it. You do not need extra requirements. You do not need to have to pre-specify the concept. You do not need labels. So you just, in a post hoc manner, in an exploratory manner, can compute these explanations and visualize the concepts which are encoded by the most relevant channels. It's widely applicable. It's highly efficient. You can get the code from GitHub. So basically, if you zoom out, what we do is we combine local XAI. Local XAI mainly focuses on explaining individual predictions, telling you where something is relevant, computing these attribution maps. So we combine local XAI with global XAI. Global XAI in the sense that it aims to explain the model. It aims to understand what concepts are represented by individual neurons of a model or by individual channels. And by combining this, we not only explain what is relevant in the input, but also how this information is represented and used by the model during inference. And this is the additional value of this global local XAI. And let me give you another example what you can do. So you can try to understand the whole inference process. So for example, here we see the prediction of a bee-eater, a particular type of bird, and we can identify the most relevant channel. For example, channel 102 has contributed to the prediction bee-eater. And then you can see, okay, what does this channel encode? In this case, this channel is encoding an animal sitting on a branch. And then you can ask yourself, what other lower layer channels are contributing to the encoding of channel 102? And then we identified channel 506 and channel 51. The one is encoding more like feathers and colors. The other is encodes like horizontal bars. And then you can also ask yourself, okay, what lower level channels are contributing to this encoding? So you can get an understanding of the whole path of inference. You can understand which channels are encoding what information and how this information is used in the inference process to arrive at this individual prediction. And another example which we did is we used this tool for debugging. So in this case, you see like an image of a safe. This is associated with the class safe from ImageNet. And you see that there is some Chinese characters in the middle, and this Chinese character seems to be relevant for the prediction. So we thought, okay, which channels are encoding these Chinese characters? We identified with our approach the most relevant channels in this region. So the 6 channels are mostly relevant in this region, which is in the middle of the image. And then we ask ourselves, for which other images these channels are also relevant. So we did kind of a reverse search. We wanted to get other images where these channels are also relevant. And we got this, and you see that for the whistle image, for the mob, for the screw, mosquito net, and can opener, these channels are also relevant. And abracadabra, they also have a Chinese character in the middle. So they also have the same artifact. So by identifying this false encoding, we could find other artifacts in the data. But what was even more surprising to us is that also the image of a puma and spider web appeared, but there is no Chinese character. So we thought, okay, but then we looked at this explanations, and what we saw is that the very thin hair of a puma and the very thin spider web look like a Chinese character to the encoding of the neural network. So there are very thin white lines, strokes on background. So from a neural network perspective, it's kind of the same whether it's a Chinese character or whether it's the hair of a puma, which means if you would like to fix the model, just removing the 6 channels wouldn't be a good idea, because you would maybe get rid of the Chinese characters, but it would also affect the prediction of the puma and the spider web. So one last note on explanation, because there was a lot of controversy about whether explanations can be trusted or not. So I think there is a lot of discussions and work that explanations are lying and that they do not pass sanity checks. So just one short note, that because we have a paper on this at the main conference, which will be presented by my colleague Leander on Wednesday. And if you want to really discuss this in depth, I recommend to go to the poster and discuss with Leander, because we think, and I think, that if applied correctly, attribution maps and explanations in general really reflect what's going on in the model and are not are really informative in this sense. We also have a lot of work on how to evaluate explanations with Quantus. We have published a toolbox with over 30 different metrics on how to evaluate explanations. So this is also a question which I'm very much interested in. And with that, I would like to conclude. So what we did in this work is to combine this dataset level XAI, focusing on the input, explaining the input, with the model level XAI, explaining what is relevant in the model, how it is represented, and how it is used by the model in the inference process. What I think we need to do in the future is also to bring into the human perspective and combine these different levels on explainable AI. And this is very important for getting more trust. So just quick advertisement of our books. The new book is open access, also discusses a lot of these new topics in explainable AI. The toolboxes already I mentioned. We have a lot of all this information you can also find on our homepage, heatmapping.org. And with that, I'm very happy to take questions. Thank you very much.
Yes, Wojciech, thanks for this very interesting talk. I'm asking the audience to stand up and go to the microphone for questions, and it happens even before asked. So there's the first question for you.
What a fantastic talk, thanks so much. I've been working on concepts, actually my thesis on how to go from importance to concept-based explanation. So it's really good to see the framework you built. And kind of looking at this talk and talk previously from Wade, it made me wonder, because we're still at the stage where we moved from importance to concepts, and we're still kind of saying, okay, we're not just going to do, instead of fixed importance, we're going to do concept importance. So what is your view on how we're going to take explanations to a whole new level, where we can talk about interactions between concepts and not just importance, but something more kind of explainable? And one example of that was Wade yesterday showed us a video where the car was moving, and then there was a textual explanation saying, I'm stopping now because I see a person, I'm accelerating because the road is clear. So very curious to hear your thoughts on how the field is going to further than just importance.
Yeah, I think it's very, very important to move from this pixel level, very low level explanations to explanations which the human can understand and which really reflects the behavior of the model. And I think with this work, we did like the first step. What I also didn't mention is that here we kind of gave names to this individual concepts by just looking at them. So we as a human said, okay, this concept 10 is channel 10 is representing red color. But I think there could be like a semi-automatic or an automatic way to really label these concepts. For example, if you would have a special data set where the concepts are labels, where colors are labels, where textures are labels, you could use this data set to automatically label these concepts and label the neurons or the channels of the neural network, which concepts they are encoding. So I think we need to move towards this more semantic explanations, and also more not only like explaining what is important in the data, but also like how this information is used by the model, and to really get an understanding on the whole inference process of the neural network.
Awesome, thank you very much. Looks like we might be able to use maybe SAM or LLMs or something like that, automating concepts.
There's one more question, Wojtek.
Yeah.
Thanks for the great talk. I just have a question about how do you see if so when we're looking at pixel level activations, we all the pixels are there, but the concepts, it could be that models actually might not learn all the concepts that humans understand. So when if in actuality there is a spurious correlation that a human can understand, this is a low performing concept. If the model didn't actually learn it, how does this method work then?
I think this is a good question. I mean, in this work, we just focus on this post hoc explanations. I think there is a different direction of work where people try to enforce models to learn certain concepts, concept whitening. And this is also very interesting work where people are trying to guide the model to learn representations better, representations which are interpretable to the human. But also for images, these concepts are more or less interpretable. For other types of data, this can be different. For audio data, for biological data, the intermediate representation of a neural network may be very hard to understand for the human because the data itself is hard to understand. So I think we also need to move towards also for this type of data to get some better understanding and to develop our methods further to give us some more understanding on the data itself.
Thank you.
Okay, there's one last question. I'm quite sad that I can't ask any questions, but apparently there's a lot of interest you raised. So one last question.
Okay, thank you. So a quick question. So in many applications, many things, we really not have knowledge of the concept. And how much it has that. So in this application, how can we do the concept level? And the follow-up question is, if we do such a concept level installation, how to verify, how to check if these concepts make sense? Thank you.
Yeah, I think, I mean, I said before that you would need either a human to make this map, or you would need to have some labeled data, or you could have an extra network trained for labeling parts of an image. So for example, if your network would be able to label the leopard shape, you could give it a label. Or if your network was trained to label color, or detect color, you could do it in a more or less automatic fashion. And I think the evaluation question for concepts is tricky. What we also play with, there is some recent work which we did on this clever XAI, is to have some synthetic data. If you have some synthetic data where you know exactly what is relevant in which way and how the things are related, you could use this knowledge for an objective evaluation. Otherwise, I think it's difficult to evaluate things, but but we are making progress also, like with this Quantus toolbox, which I mentioned. We have integrated over 30 metrics for evaluation, But I think evaluating concept level explanations is a quite new topic, and which I hope will be, will produce interesting papers in the future.
Thanks very much, Wojciech. I guess we thank the speaker again, even though there's more questions.
Thank you very much. And as I said, my colleagues are there, so please talk to them or write me an email if you want to know more about this work.
Yes, I look forward to further discussions on that whole matter. So thanks, Wojciech. We're now moving to the short orals. So we go through the paper IDs 6 through to 11. It's 4 minutes per presentation, so it'll be a bit of a speed dating kind of thing. So I would ask the next speakers to always, start being ready already while the speaker before speaking, so that we have enough time in the end to also discuss and enjoy the posters in the poster session. So without further ado, let me introduce you to the first short presentation. It's paper ID number 6. There you go. Set up here.